Welcome back to the studio. It's always good to see you back. Now, the next speaker is Markus. He's an awesome expert and a friend of mine, and it's really great to have him here talking tech in this conference. There has been always a problem with finding that one hay in the heap of the needles. And looking into the encrypted traffic, this is where Markus will talk about and explain how to do this the best. All right, Markus, welcome to the studio. Welcome to the studio, and the cyberspace is yours.
Welcome.
All right, we are here for you whenever you're ready.
Yes, I'm terribly sorry about that. Unfortunately, I left my browser tab for the conference open, so I kind of got like a double feed of what the Bernhardt was saying. So sorry about that. So my name is Markus Kont. I tune in to you from surprisingly sunny afternoon in Estonia. And I will be talking about a little something I've been working on for the past 6 months or so, and would like to kind of geek out about a little bit. So yeah, the topic is on data mining, on applying data mining methods into TLS network traffic. So where do I come from other than physical location? I work in a small company called Stamus Networks, which was founded in 2014 by two core members of OSF, Suricata development team, and we focus on building what we call SSP, Stamus Security Platform, which is a network detection and monitoring appliance based around Suricata. But it's not just a fancy front end in front of Suricata. It actually does a lot more, especially in the commercial side, in the commercial product. And yeah, we also have some open source tools available, like CERT.LV, which is basically the open source version of the security platform. Some of you from especially in the CERT and networking communities probably know Sirius, which is a nice rule management front end. You can find a Splunk app for Suricata data from us and things like that. And a few words about me. So I've been working in this company for a little bit over a year now, with a title software engineer and threat researcher, or was it threat researcher and software engineer? I don't know. We're not a early stage startup. We've been around the block for a while, but we're still small enough that, if you join up, you get a fancy title. What this basically means from my side is I spent most of my working time writing code, but I don't work on typical application development or anything like that. I usually work around data with a niche in threat hunting and stuff like that. Spent 5 years working as a server administrator in the real world. Worked 5 years as a security researcher in NATO CCDC OE. Spent time in academia. So my presentation is going to be a mishmash of that. More specifically on applying statistical analysis to detect, in this case, TLS beacons. That is the goal. And applying that on Suricata Eve protocol logs. This could work. Everything I'm talking here is actually generic enough that it can be applied on, whatever seek logs, Moloch protocol, Moloch sessions, maybe even NetFlow, if you think about it. But as you probably understood from my last slide, we are pretty much entrenched into the Suricata ecosystem. So this is basically going to be focused on that. You can see from my shirt. And everything I'm talking about is actually a work in progress. It is something that we are planning to include into the next major release of the security platform. We're still actively developing this. But like, don't tune off. This isn't like this. I really am not planning to do a vendor talk about how awesome we are. Actually, if anything, then the takeaways might be the opposite, because I'm gonna talk a lot about different gotchas and difficulties in actually trying to apply statistical academic methods on real data. So, not wasting anyone's time, let's get to the meat of things. So I assume, considering that this is a CERT conference, that most attendees know what a C2 beacon is, but I'm still going to cover the basis for those who might need could use some extra context here. So C2, or command and control, is a mechanism used by malware and threat actors in general. The idea being that you have a box somewhere in your network, a workstation. This gets compromised in some way, and once the attacker has established an initial beachhead, then the malware will essentially start calling home to some kind of backing infrastructure. And this is outbound traffic, meaning it will probably go through a lot of firewall rules. You can't really block it out. I mean, unless of course you have network proxies in there, which will help, but maybe not entirely. It's usually very periodic, with an option by the bad guys to set up some kind of a jitter, so predefined randomness. So for example, for Cobalt Strike, the C2 beacons can have a pre-configured jitter, like introduce this number of variants into the beaconing traffic. And it's mostly empty pangs, really just periodic check-ins to verify that the puppet is still alive, and the bad guy can do things with it. And traditional methods for detecting this are very IOC based, meaning you need to have an indicator of compromise. Saying that, hey, I saw this server name or this certificate or this piece of information in a stream, and I know that this is bad. But if you don't have this piece of information available, then these kinds of check-ins are very rare, and they will disappear into the background traffic. And of course, nowadays, more and more networking traffic is being encrypted, which simply means we have less IOCs to work with. Plaintext HTTP, you have a lot of different buffers and fields that we can write signatures against. But TLS is a little bit trickier, because we can actually just see very little. So what does this indicator of compromise usually look like? So this is what I personally refer to as an IOC rule for a known bad TLS server. And in my day job, I work with Suricata updates a lot. We classify rules for our customers. This rule applies to this malware family, and make the analyst's life a little bit easier. And most of our rule and method updates to our customers are like this. I would say about 80 to 90% of rules we ship from a digested emerging threats feed or something along the lines of this. Here is a bad DNS domain. Here is a bad HTTP user agent. Here is a bad TLS SNI. And this example here applies to the big sunburst campaign that everyone was excited or scared about 6 months ago. And yeah, if you see this IOC in your network, this is bad. Like this goes directly to the whatever dashboards you have. Like no need to even start analyzing this stuff. You need to have like an express way of saying, yeah, we have this. We need to kick into action now. But there's a slight problem with this one in particular, in that I'm fairly sure that this server is actually dead. Cyber criminals will reuse their infrastructure because they are running a business, just like many of us on the blue team side. So, as long as, they have a return on investment, they're not gonna, kill a server simply because it got booked. As long as there isn't an actual policeman in the server room, probably there's a good chance they keep using it. But more advanced threats and red teamers in exercises, yeah, they're gonna rotate that as soon as possible. And there's another problem with this approach in that no IOC, no alert, we don't know about it. And the fact that those IOCs got released after the APT group had been active for about 9 months or something like that doesn't really do anyone any good, because guess what? You don't have past alerts. Like if you have years worth of PCAP, you can actually parse with the updated rule set, then yeah, you will actually get an alert saying that, by the way, you were compromised 3 months ago. But yeah, good luck. Like big corporations struggle even with like a few weeks or a few days of packet capture, let alone something like a year. So can we do better? And so this is going to lead into the meat and potatoes of this talk. So C2 traffic, we're talking about very flat profiles. So here's an example of a connection ringing in perfectly every 2 hours, and a very flat profile of bytes to server, as seen by Suricata flow logs. And yeah, this is very interesting. So how do we go about actually detecting something like this? And yeah, I know there's already a whole heap of you on the other end want or like, oh great, I tuned into this and I get another machine learning sales pitch. No, actually, I'm right there with you. Having been on the analytical side of things, the main takeaway I hope that you get from this talk is I find that I personally find that, when it comes to this kind of like anomaly detection, machine learning, data mining talks, you really get 2 kinds of material out there. You get the ultra academic, going into formulas and theories and how machine learning is basically gonna, save the world or destroy it, depending on the talk. And then you get the vendor sales pitch, sales guy talks saying, again, like how we do the best machine learning ever. And yeah, I'm also tired of this stuff. So instead, I'm actually gonna run through the entire, I'm gonna run through the pipeline, at least the pipeline as I came up with it off the top of my head for this awesome beacon detection feature that we're talking about, and show you how really it isn't too much different from intrusion detection engines. In fact, machine learning, data mining, there's a reason that why machine learning isn't in the title of this slide. And that's because it's really about how to apply very basic statistical and data mining methods to build visibility into some place where you didn't have it before. So fundamentally, why is it that we are now getting more and more fatigued by the next machine learning vendor showing you that we have we will detect everything? Because fundamentally, dynamic detection methods won't replace traditional signatures. They can enhance them when applied correctly, but it's not like IDS is dead and AI is the future. No. They are fundamentally different. Signatures are static, deterministic. That means you have very clear input to output. You have a PCAP, you have a signature, you get alert. Simple. You get an alert. If it's well-written signature, it's bad. It goes directly into the dashboard. You don't even have to think about it. But you have to write the signature. Learning system, on the other hand, is something is probabilistic. It will give you an estimation. Hey, here is something that could be interesting. And usually, especially in production networks, there's still a lot of noise in this feed. But it will see things that your signature did not. You just need to actually apply some helpers and heuristics on top of it to kind of guide the algorithm for results that make more sense. And so keep just a little bit more on the machine learning. Sure, I will get to the good stuff in a second. So there are two types of machine learning widely talked about. So there is supervised machine learning, which simply means you train the model offline, you deploy the model somewhere, and then the model will classify something, saying that there's a 97.557999% chance that this is a picture of a cat. And guess what? If you wanted to classify a cat picture, then that means you need a lot of cat pictures to train on offline. Which is great if you're classifying cat pictures. You can go online and just scrape a whole heap of them, and it'll be nowadays it has been made very accessible. In the security context, especially if you happen to be working in a company like where I am, where we produce an appliance that goes into the customer networks, then that means even though everyone wants you to detect bad stuff from their networks, they're not going to give you data. That's the fact of life, because it's confidential. I mean, it would be great if, every time a big corporation gets compromised, they release all of their logs saying that, hey, this is exactly what happened. Go train some models on it to detect it in the future. But that totally happens, right? So so that's one problem. The other problem with supervised learning is that essentially it's like a signature, but it's a black box. Computer says it's bad. Why did it say it's bad? I don't know. Because model is a blob. It's a binary blob, and you have no idea why it chose the decision like it did. I guess so. So a lot better especially for network analysis is unsupervised learning, which doesn't require training, even though kinda it does, but let's not get too far ahead here. It doesn't require training, and more importantly, it doesn't really require labeled data. So you don't need a sample saying that this is a bad connection and this is a good connection. You can just take a whole heap of connections and you can cluster or organize them in many different ways to essentially get a better high-level view of them. Because there's a lot of data points and you can't inspect them all. And here we have here it's basically unsupervised learning is basically a loose collection of statistical methods, clustering, data preparation methods, this kind of stuff. And this is what the talk is also going to focus on more. Deep learning is cool and sexy, but it's not really a very good starting point when it comes to network data. Just getting training data is too hard. But we can provide some computer-assisted hunting using unsupervised methods. And here is something completely unsexy, but what is going to comprise about 90% of the data analyst's work: preparation. Because very rarely can you use something as is. Again, if you're classifying cat pictures, that's great. A cat picture is X times Y matrix of RGB values, which is exactly the format that your TensorFlows and nice algorithms are expecting. So you can almost feed them into algorithms directly. But we are actually working on sequential JSON data coming in over the wire. And before we can even start thinking about any kind of algorithmic analysis, we need to figure out how we're going to flatten this data, how we're going to build useful tables out of it, how we're actually going to do it in a streaming environment, in a appliance probe where we can't just tell the customer that, hey, but in order to use this feature, you need to have a Hadoop cluster running somewhere in your infrastructure. It's great if you do. You can totally feed this data there and do your own post-processing yourselves as well. But, it can't really be a requirement here. So we need something that works. Yeah, data preparation is the least sexy thing about machine learning. It consumes most of the time for the analyst or the developer, and however, it is the most important step because it literally allows you to do everything analytical on that data. And there are actually multiple steps where you need to apply this all the time. Yeah. So let's start from the beginning. So what is the atomic event? What is the raw input? Many people still in 2021 think that Suricata is only an IDS engine, and if you want more, then you need to set up more archive or Zeek or something else, or even still collect NetFlow. But actually, Suricata has always been about parsing network traffic fields, having great parsers for popular protocols, including TLS. Which will make rule writing much simpler. Instead of saying that match this pattern somewhere in the entire payload of the packet, Suricata parses frequently used fields into buffers. For example, for TLS, we can get TLS SNIs, TLS version, these funky little JA3S strings that I'm going to be talking about in just a second, and say that, hey, just if you see this SNI, then we know that this SNI is bad. And having already parsed all of this information means that it's not a big leap of faith thinking that, hey, like if we already have this information in memory, then why don't we log it? And Suricata does. We have this information flowing in all the time in this very nested and verbose JSON format. And we actually get multiple EU extensible event format events for every single flow we see over the wire. Here we have a flow information for this same connection. So in the previous slides, we got the TLS information. And here we have stuff like how many bytes were sent to the client, how many to the server, what was the flow age, when did it start, when did it end. And this is great. This is all the raw information we need to actually get started on this pattern detection. All right. So yeah, very sexy, right? Let's start working with matrices. And I think many people think that this is where it's leading to, and not exactly. There are no sexy trench coats in here, just a whole heap of data frames. Being a data scientist basically means you're going to be looking at tables of data all day. And, here's a quick representation of me after a long working day, looking at those tables, scratching my head and thinking like, what the hell am I going to do with all this stuff? So yeah, we had one event, and now we can start looking at many. So here we have a data frame, which is just a table of columns. Each column with a different type. So mapping the Suricata EVE events to this table to hopefully start extracting some useful information from this input. Okay, and we can construct another table from the TLS fields. Again, no sexy trench codes, just rows of data, just rows and rows of data. And this here is a very trivial example. This I pulled from a malware PCAP, and yeah, this is a very nice visual way of inspecting a lot of different records. But of course, in practice, especially on like 10 gigs, 40 gigs, we're talking about millions and millions of events. This is not inspectable. You're gonna go crazy and still not find anything. Finding needle in a heap of needles, basically. Yeah, so we need to aggregate this somehow. And we need to pick some kind of a base. So what are we aggregating over? So enter this TLS JA3S. So what is it? Again, I guess many in the SOC fields, in the SOC areas already know this, but essentially it's a fingerprinting technique that originated from Salesforce. Three guys with all whose names started with J, hence JA3. And the JA3S is the server profiling technique. So the idea there being that, before any encryption can start, the TLS server and client must establish some kind of common parameters. Hey, like what TLS version do you speak? What ciphers do you support? Like what extensions do you support? And then the server will offer a set of these parameters to the client, and this also depending on the client. And this set of plain text numbers can easily be hashed into an MD5 checksum. And yeah, and also there's a regular JA3 that is for where everything got started, which was for profiling client hashes. But nowadays, I think the bad guys have also figured out that if they don't use an obscure TLS library and just like do whatever Chrome or Firefox are doing, then the detection kind of goes away. But it's still very effective from the server side, especially here. Why did we choose this field? Because of a little thing called cardinality. What is cardinality? Cardinality means number of unique values in a data set. So if we picked something like source IP or destination IP as our aggregation point, then guess what? IP space is big, especially in IPv6. So we're going to be looking at hundreds or thousands or even millions of rows of data still in our data frame, and that's not so nice. And when the bad guys start rotating destination IPs, then that gets especially fun. However, we only get on a corporate network few thousand of those JA3S hashes on a busy, not lockdown network in a range 2,000, 3,000 distinct values. So this is much more manageable from analytical standpoint. And yeah, this is much nicer view than what we had before. We can actually make a lot more sense. We see how many events we have per server, how many different SNIs or different server names this server software is serving, how many unique addresses and how many unique destination IPs we have. That's great. So the problem here now is that TLS and flow records come at very separate times. TLS is flushed as soon as the TLS packet, the packet header is parsed. You don't need more than few bytes of data, really. I think less than 10 or 8 bytes is enough to actually parse most of the information from the TLS header, and after that already the encrypted stream starts. So Suricata will send out the TLS record as soon as possible. Flow, on the other hand, is kept in the flow table until it is properly terminated or until it simply times out. When does it time out? Depending on configuration. It can be Suricata can be configured to keep flows for a very long time, or it can be configured to keep them for a very short time. And then there is emergency mode, and all of the configurations depend, is it TCP, UDP, ICMP, whatever. So yeah, usually the flow entry comes within 15 to 20 minutes, but getting a flow 15 minutes after you saw the initial TLS record is, well, not really, not uncommon, basically. And Suricata needs to keep on hold of this flow record, because otherwise it cannot give you accurate statistics. If you want to count bytes and packets and when did the flow end, then you actually need to keep it in memory until it actually does end. So this is a problem. What do? Do we feed everything into an SQL database and run a suicide query on top of it? Yeah, I think from my formatting of this question, you already understood that this isn't. Nah. I mean, if you have this, if you're already feeding Suricata protocol logs into a SQL server, then you can really do powerful things with it. Nowadays, everyone uses Elasticsearch for a very good reason, because Suricata logs are very dynamic, and it's very hard to define a schema for it. And you have to figure, like, insertion performance is an issue, and yeah, everyone is using Elastic nowadays, which really doesn't give us this table view that we really want. And then we need to do row-wise calculations for if we want to get the time delta, for example, like what is the time between this flow and that flow, then that means we need to actually subtract the info from one flow to the other. And yeah, this is not really that scalable solution. And keep in mind, we're building an appliance. If you have a huge Hadoop cluster, then all power to you. But we need to fit this to like maximum 2 boxes. So could we stream it somehow? Turns out we actually can. That wasn't so difficult to do live denormalization of TLS struct, which simply means TLS comes first. We grab information from TLS, we cache it. Then when the flow comes later, we check the cache. Do we have TLS information for that flow ID, unique integer, and stick it into the flow entry if we can. This process is called denormalization, which simply means make queries faster on account of consuming more storage, because you have all information in just one document, so you don't need to join multiple tables, which is really slow. And it's actually surprisingly effective. The graphs here are taken from a 40 gigabit probe from a friend of ours. The scale here is actually per worker. So there is, with 10 workers, we're talking about maximum 900,000 TLS entries in the cache without doing anything special. And we are able to enrich about 97, 98% of flow logs with this information. And we get this, we have everything together. We don't need to do magical joins anymore. Great, it's denormalized. That is great. I can actually get more context. But now we have another problem. So we want to calculate a lot of measurements. For example, we want to keep all time delta values. So let's say for that set of flows, subtract the timestamp of this flow from the last one, we get a numeric value in seconds, like how many seconds have been between the 2 flows, and then we keep this measurement somewhere in memory. And we do this for bytes and packets and flow ages, and we do it per distinct JA3S, and for distinct JA3S, we do it per source IP, destination IP, and we also do it only for per source IP and JA3S because, you know, we also want to catch those tricky guys who are rotating IP addresses per request. And our maximum probe throughput is 40 gigabits, and yeah, kaboom, you can guess what happens. So yeah, so we need to limit this. So my thinking immediately was here, like we need to limit this somehow. We can't look at everything, not feasible. And yeah, so what I did, I actually pumped everything into a SQL database and built a table of counters. And I just looked at what is at the bottom, like show me all of those aggregates where, you know, we have less than this number of unique flows, this number of unique SNIs, and the results were very interesting. Again, if you have this kind of data in SQL database, this is something you can already run on top of regular Suricata data. It will produce interesting results. Let's put it this way. It might not be bad, but it will definitely be interesting. Yeah. But again, this doesn't scale. And from an analytical point of view, you know, you look at those counters; those are just arbitrary numbers I came up with from off the top of my head, and you know, it worked for one data set, but it's not going to work for another. So, IT question: can we automate it? And by automate, I mean figuring out what those numbers are really bad. Could we have a computer do it somehow? And yeah, there's a whole heap of methods called for frequent item mining. Idea being that, hey, like the top heavy hitters use almost all of the memory. They cause most of the noise. It's like they are on the top of every dashboard all the time, and we just don't care about them. We actually want to see what is happening on the bottom. So could we just get rid of the heavy hitters, and whatever is left, and that could be interesting? Yeah. So how do we actually start doing this? We start by building counters. And actually building those counters will run into the same problem, that in order to know the number of unique client hashes or SNIs, for example, we actually have to keep them in memory. So we are back at this memory limitation problem. Yeah. So enter a little thing called Kmeans. Kmeans is one of the simplest data mining algorithms. It's the first one usually being taught in any data mining class or explained in any textbook. It is very simple. You simply drop a k number of points onto a graph. The graph here representing the counts of from the last frame. So those counts are mapped into a graph that you see here. I will talk about the dimensions in just a second. You assign every single point to a cluster center, the k values. Then you recalculate all distances and then rinse and repeat the process. And the idea there being finding clear clusters of data points. And I was like, what if we get rid of the cluster of data points that consumes most of the memory and just look at the bottom stuff? So another helper for helping us do this is a little trick called principal component analysis. So remember, we have 5 dimensions. We have source IP, destination IP, flows, SNIs, client hash, unique counters. And but the problem is that's 5 dimensions. Humans have really hard time working with more than 3 dimensions. And, you know, especially if you're building an appliance and, you know, a SOC analyst might need to explain someday like what actually happened. He cannot really throw a 5-dimensional data graph to the management and say, here. No. So PCA is a nice little trick that basically just rotates those 5 dimensions in a way that we only need to use top 2 or 3 of those called principal components. It's more of a compression method, really. imagine if you look at night sky, and it's not a different sky you're looking. It's just that the planet rotates, and therefore you get a different view of the night sky depending on the time of the night. Same thing here. It's just the stars are the same. Like, you're just looking at them from a different perspective, and it makes data more intuitive because now instead of 5 dimensions, we only have to deal with 2. So yeah, and so okay. So how about we find the cluster that has most data points, that is the furthest away, we get rid of those and profit, right? If you look at the counts, you see that actually most of the data is in the bottom cluster in this big heap here. And if we drop the top cluster, we only basically drop 3 data points, which hold a lot of memory actually, but it's still not enough. Okay, I almost gave up on this method until I realized that what if we do it periodically? And again, this works surprisingly well. Just call this Kmeans periodically. We drop the frequent counters, we feed the frequent counters back in the pipeline, so we don't count the frequent items anymore, and we just keep doing this. And this is very effective. And at one point, when we have gotten rid of enough noise, we actually start tracking counters for the infrequent stuff. And yeah, it only takes about 2 hours on a live network to filter out about 99% of the traffic, to a point where within 8 hours, we are down to 1 infrequent event per second, which is amazing. Actually, the hard part is figuring out how to stop it from clustering, like what are the good circuit breakers to ensure that we don't throw out the interesting stuff as well. I'm not going to discuss this here. I need to keep some stuff for the back room, which is a fancy way of saying I'm still working on that. And yeah, on a testing QA setup machine where I'm pumping in events to a tool I wrote in Golang at the rate of 200,000 events per second, here is the memory usage. It's under control, which is the main takeaway of this picture, which is nice. I don't want to be responsible for crashing all the probes on a corporate customer. All right, so then we can start collecting statistics, finally. Do what exactly? So first of all, we need to select our features. So the features we have already covered. We have time delta, which is something we have to calculate ourselves from a set of flow events, plus other fields like bytes, packets, and ages that we can just grab from Suricata logs. And we just need to keep track of them. Then what we do is periodically we can report all sorts of different measurements that measure the flatness of these vectors. So basic stuff like minimum, maximum, mean, median, and stuff like that. Quantiles are great for just exploring and getting a quick bird's eye view. Interquantile range is a nice measurement, which is just a third quantile minus second quantile, so 75th% data point minus 25th, which is will give you a numerical measurement of like how well does this distribution of data points plateau, which is something we're very interested in. In practice, we're even expanding this to like 10 to 90% because otherwise it's a little bit just the middle is not quite enough. It's actually completely okay to call me mad now. I discovered there's a statistical measurement called median standard deviation, MAD, which is basically like standard deviation, but uses median and absolute values to make it a little bit less sensitive to outliers. Which is very important in a probe environment. Jitter calculation, for example, we can calculate the percentage to which the maximum value in the log in the vector deviates over the mean value. Of course, you have many real life problems here, like if you, for example, calculate time deltas between subsequent flows, and you have a capture problem, you don't get any flows for like 2 hours. Then what do? Like the next time delta is going to be huge. Like you have 5 seconds, 5 seconds, 5 seconds, 2 hours, 5 seconds, 5 seconds. That 2 hours is completely going to mess up the calculation, even though it was actually because, you know, there was a packet drop or something like that. It just didn't have a flow. So how do you guard against that? Well, you use quantiles. You don't use the maximum value, you use like the 99th percentile. You don't use the mean, you use median value, because those aren't really affected by these kinds of external contributors. Skewness is also a very nice measurement that gives you a numeric output saying that, hey, this of like how symmetrical a data set is, even though, to be honest, I'm not really using skew right now because skew is tricky. Skew can be undefined number, and figuring out how to deal with undefined numbers is, there was a picture of me at the end of the workday, and that was me yesterday, and that gave my girlfriend already a pretty big scare. Okay, so what do we do then? Those measurements are on different scales, so we need to push them onto the same scale. I'm not going to go too deep into it here, but you know, for example, flow counter can go to hundreds of thousands. So whereas client hash counts can go to like 10, for example, for a given data set. Then min-max scaling, I recommend looking it up. It's a very nice way of pushing all the counters into a range between 0 and 1. So it's still exactly the same data, but you scale all of your columns to the same system, basically. And there is no one magic statistic to rule them all to, you know, like, hey, like this is going to detect beacons on a real traffic. I gave up on that almost immediately. But what we can do is more of a weighted scoring. We define weights. So for example, we think that time delta median absolute deviation is more accurate representation. So lower value of this has a higher chance of the connection being a beacon traffic. Then we just apply higher weights on this. And of course, we can also apply heuristic weights here. So for example, we can build a SNI allow listing for, you know, popular domains like Microsoft.com, Adobe.com, Dropbox.com. Those are all going to pop up like cherries with this method, and they're going to go straight to the top because they have a perfect beaconing pattern. The fact that it's Windows Update really doesn't mean much to the statistical algorithm. As I mentioned in the beginning, we kind of have to guide the algorithm along the way. And the idea is very simple. At the end of the day, what we can provide to the user is something like this. I'm going to use my own testing page here to display this because I literally had a call with the front-end guys a few hours before this conference where, you know, they're still starting to build a nice and flashy UI for that stuff. But the idea is simple. We have aggregation points, we have beaconing ratings. This beacon rating actually does not mean chance that this is a beacon. This is just a numeric value that we can use to sort to make sure that entries with higher value go to the top. Because we're still working on a sample. Thresholding doesn't really work here because the numeric value is pretty high for all, but the sorting does help us prioritize more interesting entries. So yeah, coming back to the beginning, so what did I mean with this nice little meme slide here? Really statistical, like we're just building another analytics pipeline where instead of a static signature, we have some kind of a numeric parameter at the end. Instead of going in manually threat hunting, we actually have a parameter, some kind of numeric we can use to say, hey, would you mind sorting these values in a order that you think is the most relevant? And it kind of works. This is from a live traffic probe where we have access to from some friends of ours. And yeah, it will totally pick up this kind of pattern. Those of you in the know who are in the business will recognize that proofpoint.com is actually the parent company of Emerging Threats, the company that produces Suricata signatures. And they provide all sorts of security services, APIs, threat intel feeds. But we can totally pick out that this is perfect beaconing pattern. To me, this something like this says that the system actually works. There were other interesting stuff there with ambiguity, but yeah, and we can still deprioritize the whitelisted, even though nowadays you're not supposed to use that term anymore. You can define and help the algorithm along the way, saying that, hey, actually this domain is okay. Like don't filter it out. The fact that there's a good domain somewhere in the set doesn't mean that this isn't nothing bad ever happens on it. You don't want to filter out the entirety of AWS.com, because guess where all the C2 servers are nowadays. So we still want to see these entries in the data set, because they can provide value to the customer. Customer might not know that something is doing this on their network, even if it's not bad. But yeah, still. Yeah, so long story short, algorithm needs some help, and when it comes to actually doing the weighted scoring, optimizing the score, then I hope I don't get too many questions on that, because I'm still working on optimizing this right now. As I said, the picture from the previous slide of crazy Nick Cage was referencing to myself yesterday when I was, finished my working day and gave my girlfriend a big scare because I was looking at those numbers the whole day and kind of going insane. And yeah, in summary, because I'm pretty sure I'm out of time, we talked about machine learning, but I hope I gave you more of a practical sense of how these things work. Everyone says like awesome machine learning and AI will come in and save us all. IDS is dead. We need this to detect all of those things where IDS is useless. But what does it actually mean? So I hope that at least I can take this back home and get some useful insights on that. If you can find it useful for talking to the next AI vendor that comes knocking on your door. And yeah, a lot of it about just data preparation, because data preparation, data reformatting, enrichment is the most important part of the whole thing. Without this, you don't have anything. Getting rid of noise, and finally the beacon scoring, which I admit is still work in progress. And yeah, the fancy term is building computer vision. Human looks at the set of flows and says, this is a beacon. How do we actually make a computer do the same thing automatically? And I hope everyone found this interesting, and I thank you.
Markus, thank you so much. I skipped the Q&A just to give you more time because of the valuable information you've been providing to us. Now, I mean, Q&A is still there. If you are available over Discord channel, there are questions pouring in. I mean, your talk has sparked a lot of questions. Some of them, I will not take them here because your answer might be just too long for this. And maybe it's more precise if you could answer those in the Discord channel. It would be highly appreciated.
Yes, I am in the Discord, so I will take a look and try to answer the best I can.
Thank you. Thank you so much. Thank you for the extraordinary and in-depth talk that you gave us. This is really, really valuable. Thank you so much.
Thank you.
Thank you, everyone. I hope you have enjoyed the session so far, but stay tuned. Just after a little bit less than 5 or 6 minutes, actually 6 minutes, we'll come up with the next talk right for you. Thank you, and see you very, very soon.